The first algorithm that we're going to talk about to create a minimum spanning tree is Prim-Jarnik's algorithm. Now this was initially discovered by Czech mathematician Jarnik in the 1930s, and then later it was rediscovered by computer scientist Prim, and then by Dijkstra in the late 1950s. So sometimes this is called Prim-Jarnik's algorithm, other times you'll see this called Prim's algorithm or Prim-Dijkstra's algorithm, but these are the same. Now this is similar to Dijkstra's algorithm for creating a shortest path tree, but again, a minimum spanning tree and a shortest path tree, these are not the same thing. So while we'll have a similar approach, we are constructing something different. So we've got a difference in how we're constructing this tree still. But the idea is we pick some arbitrary vertex S. It doesn't matter where we start because every vertex will belong to the minimum spanning tree. And we'll grow a minimum spanning tree outward as a cloud of vertices. So eventually all vertices will belong to this cloud and we'll maintain a minimum spanning tree of the vertices which belong to that cloud, beginning with the initial vertex S. And with every vertex we store a label, like a distance label, but here this does not represent the distance from a vertex to the starting vertex. Instead, this represents the distance from this vertex to any vertex already in the cloud, either the starting vertex or any other vertex already in the cloud. So this represents the smallest weight of an edge. So this is the main difference in how this differs from Dijkstra's algorithm for a shortest path tree. Instead, here we're finding a minimum spanning tree with Prim-Jarnik's algorithm. So at every step, we'll iteratively take some vertex which doesn't belong in the cloud yet, which is outside the cloud, take whichever one has the smallest distance label, the smallest weight of an edge connecting that vertex to a vertex of the cloud, and then add that vertex with the smallest distance label to the cloud. As soon as we add U to the cloud, then we relax all incident edges. And the edge relaxation step differs too in order to maintain that the labels we're storing are the smallest weight of an edge connecting it to a vertex in the cloud. So if we have edge connecting U to Z, and since U has the smallest distance label, we add U to the cloud next. And when this edge is relaxed, we set the distance label for Z to be the better of either whatever we had before for it already, meaning Z connected to some other vertex in the cloud, not U, with minimal edge weight. Or, now that U is in the cloud, maybe Z connects to this cloud in a better way via vertex U. So in that case, if this is edge E, then we would take the weight of that edge E. So we're not accumulating edge weights. We're not including the distance label of U in this at all. This is our main difference here. We're just taking the edge weight itself. Okay, so formally, this is the pseudocode for that algorithm. You'll notice it looks very similar to Dijkstra's algorithm. We have a heap-based priority queue which keeps track of the vertices not in the cloud yet. We do start at some arbitrary vertex. It doesn't matter which one we begin at because they'll all be in the minimum spanning tree ultimately. And for that arbitrary starting vertex, we set its distance label to 0, and for every other vertex, we set its distance label to infinity. We'll maintain for every vertex 3 labels. Its distance, a parent, which is initially null, but we'll use this to keep track of when we update a distance label and find a smaller weight edge connecting it to a vertex in the cloud. We'll set its parent edge so that we can recreate what that minimum spanning tree is when we're finished. And we'll also keep track of a locator. Now this locator represents when we insert this vertex into the priority queue based on its distance label, we maintain where that vertex belongs in the priority queue so that we can later, when we update the distance label, update where it belongs appropriately in the minimum heap. And then we'll go through every vertex which is not in the cloud, meaning this vertex is in the priority queue, and take whichever one has the smallest distance label and relax all edges which are incident to it. The only difference here is in how we relax an edge, specifically that what we are evaluating, again, this is if we have some vertex U, which we've just added to the cloud, and we're relaxing this edge E, which connects U to vertex Z, we set Z's distance label to be the better of either whatever it was before or the weight of that edge, not an accumulation of weights, but just the weight of this edge. And if that value is smaller, we update the distance label for z, appropriately set its parent, and then update where z belongs in the priority queue since its distance label is updated as well. So because these are the only changes we make in comparison to Dijkstra's algorithm, the total runtime for Prim-Jardink's algorithm, we have the same analysis argument, is n plus m times log n. So you can refer back to the video on Dijkstra's algorithm to get an analysis on this. And because we can assume that we're working with a connected graph, so in that case, for a connected graph, the number of vertices n is big O of the number of edges m, or equivalently m is big omega of n. So this effectively means that for a connected graph, m is the dominant term between n and m. So in that case, when we put this in big O notation, you may also see this written as m log n. Let's see an example of this now on a small graph. So we want to create a minimum spanning tree of this graph following Prim-Jardink's algorithm. We have edge weights associated with each edge here. And we're going to start at any arbitrary vertex, so let's just suppose we start at A. It doesn't matter which vertex we start at. So we'll assign a distance label to A as initially 0 and infinity for everyone else, and then grab whichever vertex has the smallest distance label, add it to the cloud, so that will include A initially. When these edges are relaxed, we update the distance label for B, C, and E to be 2, 8, and 7. This is based on the weight of this edge connecting that vertex to A. Now in this remaining graph, we'll take whichever vertex which is not in the cloud, these are those vertices in blue, so the vertices in blue are in that priority queue. We'll take whichever one has the smallest distance label, which in this case is B, and we'll add it to the cloud next. When this is added to the cloud, we relax all edges, but this is really where it becomes apparent how this differs from Dijkstra's algorithm, why this is finding a minimum spanning tree and not a shortest path tree, is that when we update these distance labels, we are maintaining not an accumulation of edge weights, but rather just the weight of this edge which connects C to a vertex in the cloud. So now that B is in the cloud, we find that there's an edge connecting C to a vertex of this cloud, which has weight only 5. So we find something better than what this edge was providing. Oops. So we update C's distance label to be 5. And for D, we can do better than infinity. We can set its distance label to be 7. So now the remaining vertices not in the cloud yet, we take whichever one has the smallest distance label, which is, in this case, C, and we'll relax all incident edges. So from C to D, this doesn't improve anything because 9 is a larger value than 7, so we won't use this edge. But from C to E, again, we won't improve anything because this edge would give a label of 8, and we already had 7, so this doesn't help us all. Oops. Okay, so now that we have the following vertices in the cloud, we take the remaining ones and take whichever one has the smallest distance label. Now in this case, we could choose between D or E because they both have the same value. It doesn't matter which one. We can break ties arbitrarily. So suppose we chose D. So in this case, we relax all incident edges. So we have this one, which we haven't yet considered. And this gives that we can update F's distance label to be 4. This is better than what we had before at infinity. And now the remaining vertices, we pick whichever one has the smallest distance label, which is F. And when we add F to the cloud and relax this edge, we'll find that we can get to E in a better, that we have a better edge that gets to E. So instead of 7, we'll have 3. Let's see that. So once this edge is relaxed, we update E's distance label, so we're no longer using that other edge that we were before to get to E. And now we add the remaining vertex to our cloud, and we have no other incident edges to consider. So those edges which are shown in red induce a minimum spanning tree. And again, note that this is not a shortest path tree. This is a minimum spanning tree because we're including all vertices of the original graph and only the least number of edges that we need to, and specifically those edges where if we were to add them all up, we get a minimum total sum. However, this minimum spanning tree is not a shortest path tree. And to give you an example, look at a path from vertex A to vertex E. The shortest path from A to E goes through this edge, and it costs 7. In the remaining minimum spanning tree, we would have to go through these edges, which has a total cost of 16. So this doesn't give the shortest route from one vertex to another vertex. It just guarantees that the tree which we construct has minimum total edge weight globally for that entire tree.